So in physics, we will often make a position versus time graph. In science, we usually put time on the x-axis. So you put position on the y-axis, time on the x-axis, and the um, you're measuring the change in position of an object over time. So there's a couple of things we can see from this. The first is at any point in time, we can figure out what the position is by just looking at the y value for that given x value. So like, let's say I'm looking right here, let's say this is like b equals, I don't know, 6.1. I can find my position by going over here. And I could say that at t equals 1, x equals like 2 point, I don't know, call that 2.7, right? Oops, sorry, t equals 6.1 seconds, excuse me. T equals 1 would be over here. Okay, so first of all, we can read the graph like that. That's fine. Hopefully that makes sense to you guys. But there's other things we can get from this too. We know that velocity is a change in position over change in time. So basically, let's say we want to find the average velocity between 2 points here and here. Well, okay, my change in position is just going to be how far they've moved between this spot and this spot. Let me start that over, sorry. Between this spot and this spot, right? I've changed my position from this position. Maybe it's like x equals, it's actually about x equals 2. And then I've moved it to x equals negative 2. Right? So I've changed my position between 2 and negative 2. And my change in time is on the bottom. So I've changed my time from, I don't know, maybe about 7 seconds to like, about 7 seconds. This is probably about 12 seconds maybe. So I've changed my position between 2 and negative 2. I've changed my time between 7 and 12. I can figure out my average velocity as change in x over change in t. So I'm going to call this my initial point. I'm going to call this my final point. And I can say that final minus initial, negative 2 minus 2 over 12 minus 7 gives me negative 4 over 5. And that's the slope of my graph, which is also equal to my velocity. So basically, you guys probably learned in math, slope is rise over run. Amount that you change your y over amount that you change your x. Because we put position on the x, or on the y-axis, excuse me, and time on the x-axis, rise over run is just going to give us velocity. That is our change in position over our change in time. So finding the slope is what we just did. This is y minus y over x minus x. As long as you keep the order consistent, the order doesn't matter for this. However, if you wanted to be a stickler about it, we should do this as y final minus y initial over x final minus x initial. So this is how you get the slope of your graph, and the slope of that graph will give you your velocity. So in other words, velocity is the slope of a position versus time graph. Because, again, slope just measures change in y over change in x. By putting position and time on these two axes, we can make sure that the slope will always give us a velocity. So I would like for you guys to take a look at this graph that we just talked about and try to describe in words what this object's motion will look like. So like, let's imagine that there's a thing in front of you and I'm describing its motion with this graph. So try to think and describe in words what this object will do. So pause the video, think about it. We'll come back here in a moment. Okay, welcome back. So let's try to think about what this object's motion will look like. So we start at time 0 at position 0. So we start at 0. And then for about, I don't know, like 3.5 seconds maybe, this object moves upwards in the positive direction. So here we've got a positive velocity from here to here. And notice the slope of this line is not changing, so I could say it's got a constant positive velocity for about 3.5 seconds. Then here, notice my position is not changing as the clock continues to go on. It's a flat line, and the slope of a flat line is 0. And we are going to stay stationary for about, I don't know, this looks like maybe about 8 seconds in, we'll call it. Okay, so this object started moving in the positive direction. For about 3.5 seconds, it walked forward until it was about 3 meters away. I'd call this position at about 3 meters. chilled out there for about 4.5 seconds. Then it starts moving in the negative direction. So here we've got a constant velocity in the minus direction. Okay, so now basically we've turned around and we start moving backwards. We're going to keep walking until we reach here. That's probably about -3 meters. And notice we pass by the starting point. So notice we have walked forward, stopped for a minute, turned around, passed by the initial starting point, and now we're down here about 3 meters behind our starting point. Then, again, position is not changing because the clock ticks on. Our velocity here is going to be 0. And we stay here from about probably like 12.5 seconds. And then here is like about 17 seconds probably. Then, from about 17 seconds to 20 seconds, we have a velocity in the positive direction that is also constant. Right? The slope in all these cases of our graph is not changing. So this is what the object motion would look like. So basically, we have a thing starting at the 0 point, moves forward for a couple seconds, stops there for a while, turns around, passes by the starting point, moves behind the starting point, chills out there for a minute, starts moving back forwards, and then stops at the starting point again. Okay, so that is how we can describe in words this object motion. So if you guys could please pause the video again. We want to try to figure out what the average velocity of this object is between all the different points in time on this graph, and then find its maximum position away from the 0 point. So if you guys could please find the velocities between t equals 0 to t equals 4, t equals 4 to t equals 6, t equals 6 to t equals 8, and t equals 0 to t equals 10, please. So mathematically, please find the velocities between all these points. Okay, welcome back. All right, first thing first, let's mark where all of our spots are. Here, oopsie. Oh, that's not what I wanted. Here is t equals 0. Here is t equals 4. Here is t equals 6. Here is t equals 8. And then here is t equals 10. Okay, I'm going to also try to figure out what my x coordinates are at each of these points as well. So at t equals 0, my x is about 2. At t equals 4, it looks like my x is about 8. At t equals 6, my x is about 0. At t equals 8, my x is 0. At t equals 10, my x is 0. Okay, remember, to find our velocity, we want to find the slope. And slope is rise over run, which is the same as saying delta x over delta y. Sorry, I'm so sorry, excuse me. That is delta y over delta x. Forgive me, it's rise over run, not run over rise. And so for us, we can say that is our final position minus our initial position over our final time minus our initial time. All right, so let's go ahead and do this for all of these points. Here, our final x is 8, and our final t is 4, so that's 8 over 4, minus 2 over 0, that is 6 over 4. So over here, our slope is positive 3/2. Between t equals 4 and t equals 6, it's final minus initial. So our final is this, our initial is this. It's going to be x is 0, excuse me. Final x is 0, minus our initial x is 8. Final t is 6, minus our initial t is 4. 0 minus 8 over 6 minus 4 is going to give me -8 halved, or -4. So v equals -4 for this piece. Now, that should make sense, actually. We have a negative velocity, which is going to give us a, the object moving downwards, right? A negative slope. We also have a steeper line here than we do here, right? So 4 has a higher magnitude than 3/2, meaning this line is steeper. We're getting a larger magnitude for our velocity. Okay, let's do it for this part. That is 0 minus 0 over 8 minus 6. That's 0. So our velocity is 0 down here. And between t equals 8 and t equals 10, we also have 0 minus 0 over 10 minus 8. Final minus initial. That is going to be 0 as well. So for here, that velocity is 0 too. Cool. All right, let's now look at our last one, which is t equals 0 to t equals 10. Let's look at the whole crib. So between this point, I'll use a different color for this. Between this point and this point. So again, slope is rise over run. That's going to be final x minus initial x over final time minus initial time. My final x is 0. My initial x is 2. My final time is 10. My initial time is 0. I get negative 2 over 10, or negative 1/5 is my velocity. And check this out. If I draw a line from here to here, notice it is not a very steep line, but it is negative. So got a low magnitude, pretty low velocity. However, it is negative, moving in the negative direction. So that works out for this question. That is how we can find our velocities between these points. There's another question it asks. It's an easy one. What is the object's maximum position away from the 0 point? Our maximum position is just going to be the highest y value we get from this graph. That's going to be this. So our maximum position is x equals 8 meters, which happens at t equals 4. So this thing is furthest away from our 0 point at 4 seconds before it turns back around. Cool. All right. So here's the thing. Real objects almost never have straight lines. A straight line is implying that it takes you 0 seconds, actually 0 seconds, to go from moving this fast to moving this fast. That is not possible, right? That any object is not going to be able to turn where it's able to change its velocity in 0 seconds. It's always going to take you some period of time. Some things can turn on a dime pretty easily and change their velocity in a low period of time, but that's not 0 seconds. Likewise, on a velocity versus time graph, you will never see a straight vertical line. First of all, the slope is undefined of a straight vertical line. But second, more importantly, that straight vertical line is saying in 0 seconds, you are moving some number of meters, which means you are teleporting, or you're moving with infinite velocity. So anyway, sorry, a straight horizontal line, my point, has a slope of 0. It's not moving. A straight vertical line means it's moving infinitely fast, which is not possible. Okay, so when we have a curvy position versus time graph, if it's curvy, that means that, if it's curvy, that means that it is not moving at a constant velocity. That should make sense. Whenever we, change velocities are slope. So whenever the slope of this graph changes, which is what a curved line is, we're changing our velocity, right? So we could use calculus, given the function of a graph. We could use calculus to figure out our instantaneous velocity at a certain point. But instead, we could just draw tangent lines. Now, basically, how you draw a tangent line is pretty simple. Imagine I choose, I'm looking at this point here. Imagine I choose a point here and a point here. I can get a decent approximation for the slope at that point by choosing 2 points that are close to it. I could also move those 2 points closer together, and I get a better approximation. I could move those 2 points closer and closer together and get a better approximation. I could move those 2 points like right on top of it, basically, and get a better approximation. So I can get closer and closer and closer and closer and closer to an approximation of where this line's going to go and just kind of eyeball it and say its velocity is like this at this point. This is called a tangent line. Calculus will give us a function by taking a derivative. Calculus will give us a function that actually will measure a tangent line. However, we're not doing calculus here, so we're going to eyeball it. We can draw tangent lines onto this by just kind of eyeballing. Its velocity is kind of like this. At this point, it's going up kind of like this. Basically, what I'm doing is I'm choosing 2 points that are close to it and trying to draw a line between those 2 points. It is a decent enough estimate. That one was kind of bad. Like between here and here. Look at this. It's our velocity here. So basically, if I were to freeze time at exactly this spot on my position time graph, I could estimate its velocity by drawing a tangent line. Or we could use calculus to find the actual function. We're not doing that in this class, though.